you all. My name is Nicholas Opoku, as mentioned, and my presentation is on understanding the beauty of mathematics through its application to how the immune system interacts to tuberculosis. The outline for the presentation is we look at the background to the research, the main organs of the human body, the general interaction of what happens when a pathogen invades the human body. Then we now specifically come down to how the immune system interacts with the MTB. Then we link it to the mathematical framework, develop the mathematical findings, and then look at some reference. When we look at this image, it shows us how the human body is. And we always know that the human body is an organized structure from the head to toe. And running through the human body are what? Cells and organs. But aside these cells and organs, we also have viruses and bacteria getting their way into what? Into the human body. But the immune system helps the body to fight these viruses or bacteria. And they do that through these main four organs. And they use the lymph nodes, the thymus, the spleen, and the long bones. What the lymph node does is produce the T cells, which we all know. And then the thymus provide a home for these T cells. The long bones is what is responsible for generating blood in our human body. And when it does so, the spleen filters the blood so that the body will get the appropriate blood to function. Now, when a virus or a bacteria invade the human body, as you can see with the yellow image, the first line of action it meets is what we call macrophages. What the macrophages does is it engulfs this virus or bacteria and displays its viral antigen, like the image as a ball. I actually needed a pointer, but sorry for that. As a ball, and when it does that, it signals the T cells so that they come into play to fight this virus in the body. When the T cells come in, they divide into two, known as the B cells and the killer cell. What the killer cell does is it's supposed to come in to kill the infected macrophages, but before it does so, it needs a signal from the B cell. So the B cell produces what we call the plasma cell to produce an antibody to attach itself to the infected macrophages before the killer cell now destroys the infected macrophages, and the body will now come back to what? Normality. Now when it gets to that of the immune system, the same thing happens. And this time let's watch a short video as to how it's being done. Tuberculosis is a really dangerous disease, and as we all know, it is spreading very fast. So when you look at the world population, about 1/3 of the entire population is suffering from tuberculosis. And the virus or the bacteria that causes it is the Mycobacterium tuberculosis. So if 1/3 of the world population is suffering from tuberculosis, it means the rest of the 2/3 are what? At risk of what? Being infected. Hence, now just as we realize from the general interaction, when an individual having the bacterial cause, then it means that anyone closer to that person is what? Is at risk, because the individual spreads the virus into the air, and an uninfected person inhales it, and the place in which they love to settle is the lungs of the human body. So when they do so, the immune system now calls in the macrophages whenever they are swimming. So that's the macrophages coming in to engulf what? The bacteria. When they do so, they place that individual in what we call the latent state. That means the macrophages have been able to hold them up, and that individual will not be able to spread it. But the nature of the bacteria is such that they reproduce very quickly, and they put pressure on the macrophages. So the more and more they increase, then that individual is moving from the latent state to the active state. So when that individual is now at the active state, the individual begins to cough very heavy and still have some kind of fatigue. And when that individual coughs, you can see at least blood and stuff in it. So that's the switch. Now the bacteria is all over the body of that individual. The individual begins to find it difficult to do what? To breathe. And the reactivation is as a result. If someone who smokes or drinks or tries to have HIV virus, the switch is very fast. So when that individual happens to be in that mood, that individual is in the active state, and when he coughs, we are all at risk. For the sake of time, let's just try and switch it. And the good news is, there are various drugs attached to it, and when you go, you will be placed on it for 6 months. But we mathematicians are saying it is too long to have tuberculosis and be placed on a drug for 6 months. So how can we help? And to do so, then it means that we have to try and create a model that will help. So we generate this beautiful mathematical model that incorporates the human immune system, the bacteria, and the macrophages itself. So these are our T cells that is being produced by the human body mathematically. So it differentiates, as we saw earlier, into the B cell and then the T cell. And the T cell also produce what we call cytokines. Sorry for those words. The cytokines are the interferon gamma, interleukin 2, and tumor necrosis factor alpha. When they are produced, it means when the bacteria gets interacted with the uninfected macrophages and becomes infected, then they signal this T cell to come in to help the human body. This interferon gamma comes in to activate, and we realize that through mathematics, after performing the calculations, that the interferon gamma plays a bigger role. So our concentration should be on what? On that one. So these are the differential equations from that model. Forget about it, it's scary. So we have something called the basic production number, and it tells us how one infected macrophages affects the other one in the immune system. And so we realize that when we are able to cut the interaction rate between one infected macrophages and the other, then it can help keep that individual in a latent state for a very long time. So those who do epidemiology, we know that the square root is because we need 2 populations. So let's just learn something new here. We need 2 populations before the tuberculosis virus can spread. And this is a beautiful 3D contour graph that shows how we can eradicate the disease. So when we look at it, this is our interaction parameter mathematically. So when we shift this to 0, then it means we have cut off what? The interaction between the macrophages and that of what? The uninfected one. So this is how beautiful mathematics is. So performing the numerical simulation in this way, using a data from the World Bank, we have this. And then this is the latent state, showing us or trying to give more evidence to what happened when that individual is in the latent state. We observe that even if the number here increases, the rate at which the graph is growing exponentially is steadily, is very slow. Now, the main idea, this is the switching time, what we refer to as the switching time. If it would take 6 months for us to cure just an individual suffering from tuberculosis, then what can we do? We observe that if we can produce a drug that will concentrate on the interferon gamma, represented by omega in our mathematical work, then we observe that when omega is small, that is when the strength is small, then the time it will need, here we were working in days, is 100 days. That's 10 times 10, so 100 days. But if we increase omega to say 0.5, that is if the strength is being increased, then the days to cure that individual begins to what? Begins to reduce to say 70 days. Now if omega is further increased to 0.7, we realize that the days are also what? Being reduced. And when we further increase it to 0.9, realize that it's taking at least 50 days. So if our pharmaceutical companies can then now concentrate on the interferon gamma as we have proven it mathematically and produce a drug that will strengthen it, then definitely we will not spend 6 months trying to cure just one individual suffering from tuberculosis. These are some of the references I use, and thank you very much for listening.